Okay, so today I'm actually going to finish up pretty much all of the basic features of event graph methodology. One of the reasons why I am particularly fond of it is that it's actually quite simple. Remembering that simple isn't always easy. So it's simple and yet, as you may be discovering, if not now, shortly, that it can be challenging to use as a methodology for creating a model. And let's put this on the screen. Okay, so so today the two additional features are going to be what's called a canceling edge. So far we've had just a scheduling edge. So we'll see what a canceling edge is about. And then we'll see parameters on edges, which is going to be basically analogous to having parameters in methods. So far, the events that we've been using have not had any arguments. But as you saw in the computer assignment, that when you take events and then use them in a SimKit context, they become methods. And since methods can have arguments, then you would think that events can have arguments, and in fact that is the case. So just some examples of passing arguments through the scheduling edge is the event graph equivalent of the for loop. I think for historical reasons, the guy who came up with the idea of event graphs was very much a minimalist, so he didn't want a lot of stuff in them. That's why they're nice and simple. And so things like for loops were not built into it. In other words, and there's a good reason for that. So even though when we're implementing it on the computer, you can actually put a for loop in, you just write it in. Using pure event graph language, there is no for loop. Part of the reason for that is that everything in an event happens in zero simulated time. That's something to really keep in mind. Again, all state transitions occur in zero simulated time. They instantly go from one value to the next. And so if you had a for loop inside of an event, then you'd have a whole bunch of things happening simultaneously, or happening in zero time. And one could argue that, well, maybe it should have a for loop, but the fact is that it doesn't. So the guy who came up with this said no for loops, but if you want a for loop, then you can create one using events, and we'll see what that is about. One particular application of that is a situation in which we want to schedule a certain number of events at the start of a run. In other words, by itself, the run event with a capital R is the only event that goes on the event list at the beginning. But there are situations where you say, well, I want some additional events that the modeler has defined, and I want them to be on the event list at time 0. And how do I do that? Well, one way to do that is to use the event graph equivalent of a for loop. We'll see what that's about. And then another application of using having parameters on the edges is this simple inventory model that we'll talk about. Okay, so canceling edge. If you remember, scheduling edge is something where if this were a scheduling edge, this would be when event A occurs, it puts event B on the event list. And so far we've seen a few examples of this. But the only way that an event comes off the event list once it's been scheduled has been when it bubbles to the top and the event list algorithm processes it. In other words, the event list logic says, okay, you're the next event to occur, and that's how you'll get off the event list. But there are situations in which you want to say, well, at a certain time, I thought that this event should happen, but later the model changes its mind and says no. So one way to think about that, if you remember, when we were talking about scheduling edges, one little thought experiment was if we have an event that a missile gets launched and then that would schedule another event sometime later that it would impact, the question might have come up in your mind was, what if the missile gets intercepted? Then what happens? So remember, and as far as the model is concerned, events on the event list are just going to get processed. So again, just sort of thinking about how this could occur. If there were some event that caused the missile to be destroyed before it impacted, and as far as the event list is concerned, that impact event is still on the event list. So you would want to take that off in that case. That is, in the case that somehow this event, missile intercepted and destroyed, occurred before the impact event, then you would want to take that event off the event list because, again, as far as the model is concerned, that impact would be there. And then if you didn't do that, then what would happen is, well, we destroyed the missile, but the impact still occurred. And obviously that's not what you want. Okay, so a canceling edge is a way to achieve that. So what a canceling edge operates like this is that it always is it happens as a result of some event, because events are really the only things that happen in this world. And so this is the canonical way of looking at it. And when this event A occurs, then we have a Boolean condition as well. So if that were, why does it keep giving me a black pen? I don't want that, I want a red pen. When event A occurs, then there's a certain condition. And if that condition is true, then what happens is the earliest occurrence of a previously scheduled event, in this case we're just calling it B, is just simply removed from the event list. Just as a scheduling edge will only schedule one event at 1 or 0, depending on the Boolean condition, likewise the canceling edge will cancel 1 or 0 events depending on the Boolean condition. So if there are multiple events B, then only the first scheduled one gets removed. That's how it works. So if I want more, then I'd have to, if I wanted, say, all of them, then I would have to somehow have this event repeatedly rescheduled. But for right now, again, the rule is when one event occurs, then if the Boolean condition is true, then the next event is removed. The next event, not the next event of any kind, the next event of, in this case, the next event B is removed from the event list. And by next, I mean the earliest scheduled one, not the one that was scheduled first, the one that was scheduled to occur first. So in this case, if A were the event attempt intercept, and the Boolean condition was intercept successful, and B was the impact event, then you see how that would meet the situation that was described. In other words, if the intercept is successful, then the impact event is removed because you don't want that to happen. On the other hand, this also takes into account the fact that the intercept was not successful. So if the Boolean condition is intercept successful, but that evaluates to false, then the impact event would not be removed, and it would still happen. And again, that's what you would want to. That's how you'd want it to be in the model that you have. So here's a simpler example of that. You've all, by now, hopefully, done your basic arrival process. And now what you may have noticed if you forgot to do the stop at time, you may have noticed that it kind of goes on forever and you have to kind of Control-C it out or hit the little red square. I don't know if that's happened to anybody. But if you want to see that in action, just kind of comment out the stop at time thing, and then it just goes on forever. And that's the logic of the arrival process, is that it goes forever because there's nothing to stop it. And so you might say, well, what if we want it to stop? Well, there are a couple of ways to stop it. But let's say that we wanted to stop it after a certain amount of time. Say, okay, we want the arrivals to come, but then after a certain amount of time, we want them to stop. Okay, can you think of a use case for that? Exactly, yeah, that's, so a store opens at, 9 and closes at 5. And, how do these usually work? When a store closes, there are typically some annoying customers that are still inside. So as far as the model is concerned, you can either kind of blow the whole thing up, or you can kind of do what most stores do, which is you sort of lock the door and have a guy there, and then when people come, you say, sorry, you can't come in, it's closed, but then when people try to leave, you unlock the door and let them out. So the way the model would be running in that case is you don't want to just sort of stop it at that time. You want to stop the arrivals and then let all the customers that are inside out. Okay, so this would be a mechanism for how you would do that. See, here's the dilemma is that it's actually a little more straightforward to stop after a certain number of arrivals. And the way to do that would be to simply put a condition on the rescheduling to say that if n was the number of arrivals, and if that were less than some value, then you simply cancel this. That would be a way of doing it, of saying we only want to have X number of arrivals, and then we want to stop it after that. But this isn't that situation. You see how that the store example, the store use case, would not allow, that wouldn't be appropriate, because that would say, well, we only going to have 50 customers today. So if the 50th customer comes, but you're still open, then the model isn't, taking that into account. So here we're saying, okay, the store is going to close after a certain amount of time, and then we want to cut off the arrivals. So here's how we do that. From the run event, we simply schedule another event. We'll call it stop or stop arrivals or something. Actually, stop is not the best name for this, but again, the names are arbitrary. It works fine. We schedule that after our time, and then when that occurs, we simply cancel the first arrival. But as you have observed, at any given time for the arrival process, there's only one arrival event on the event list. In other words, you don't put them all there at once. You just kind of put them on one at a time. And each guy says, okay, the next guy's coming after a certain amount of time. And then once that arrival is canceled, then it just doesn't happen again. Okay, so is that fairly clear, I hope? Okay, now the almost final, I think, I'm not talking about priorities yet, but that's kind of in the reading. We'll touch on that. The priority thing, it comes up occasionally, but in situations where we're mostly using continuous random variables like exponentials, gammas, uniforms, normals, the priority thing typically doesn't come up too much. So we're not going to talk about that yet. Again, it's in the reading. But now let's look at parameters. Again, if you think of the SimKit equivalent of an event and as a method, and since methods can have arguments, then an event could have an argument. And that is often a case where, a situation where it's useful to do that. And so, in addition to our regular scheduling business, we have a situation where we have an event with an argument. And just as if we were invoking that method, we would need to pass a parameter. Or else, the compiler would object. Now, in the way that SimKit works and the way that event graphs work as well is it's a little bit looser than that, in that we'll see how that works. But basically, in terms of syntax, the idea is this, that I have an event, B, and it has an argument K, and that could be one or more variables in the list. So when event A occurs, then again, we have the Boolean condition. If it's true, then we schedule event B with a delay specified by the time on the edge. And again, if the Boolean condition is left off, it defaults to true. If the time is left off, it defaults to 0. But now we have an additional piece here, and that is an expression J, which needs to be coherent with the argument. In other words, if K is an integer, then J has to be an expression that evaluates to an integer, just as if we were invoking a method. If we have a method that has an argument that's an integer, we would need to call it with a parameter. And when we call it, we'd have to pass an expression which evaluates to an integer. So when event A occurs, if the Boolean condition is true, we schedule event B with a delay of t, but then here's the thing, is that, and this is what's different from invoking a method in a regular program. When the event B does occur, its argument is set to the value of the expression J when it was scheduled. So in other words, this parameter is like a time capsule. In other words, one of the main uses of this is that it passes information about the state of the simulation at one time to a future time. So typically events often occur in the future. And so when this event B occurs, then its argument is equal to what this expression was when it was scheduled. And the reason that's, okay, so that may seem a little vague, but here's the thing, is that when this event occurs, which again could be in the future, the value of if I were to evaluate this expression when B happens, it is likely to be different than when it was scheduled. And if you're just invoking a method directly, then that's all you get. In other words, when I invoke a method, the argument is, the parameter that I pass to the argument is whatever value it is right now. But the use of this is to take this expression is just some information about what the state of the simulation is when this event was scheduled.
So J is not a constant.
Pardon me?
J is not a constant.
No.
It changes throughout the.
Well, again, J is like an expression. Remember, again, keep in mind the difference between a formal argument, like when I define a method, what I have is a formal argument, and that can just be like one variable. Whereas an expression can be, it can be either, it could be a constant, it could be typically, if we're doing this, it usually doesn't make sense to pass a constant, because if I have a constant, then I can just use that constant. Typically, it's an expression, and by expression, I mean it could be a single variable, or it can be some combination of variables.
So J is evaluated when B is scheduled, not when B is called.
Exactly, exactly. Thanks, Ed. You put it better than I did. So, J is evaluated when B is scheduled, not when B occurs. So, and we'll see an example of that in the inventory model. We'll look at it in a second. So here's one example of this, which actually doesn't involve any time. But remember, I said that built into event graphs, there is no concept of a for loop. But what if I wanted to have a for loop-like construct? So basically, here's how you do it, and this is just sort of a pattern that happens in a few situations. So basically, what this is going to do is I have a parameter. Okay, now here I'm using parameters in kind of two different ways here. So I want the init event to happen m times at the very beginning. Okay, so that's a simulation parameter. A way to implement that is to define an event, and I'm going to call it init. You can call it whatever you want, but it's going to have an argument, which I'll call I. And if you remember, I is a very common variable that's used as the index for a for loop. So that's kind of by design. So the idea here is that run will schedule init, passing it, in this case, a constant 0, because basically this is like the initialization piece of a for loop. So we're going to start at 0. So 0 is an expression. But then when init occurs, it takes its argument I and schedules itself passing I plus 1. And the Boolean condition is that I is less than m minus 1. So if you were to execute this, then the init event would happen exactly m times. Now you may be wondering, and if you're not, I'm going to wonder for you, this condition, you may wonder, shouldn't this be I less than m rather than I less than m minus 1? Because if this were a for loop, the condition would be I less than m, right? But it turns out that because of the way that this gets processed, the condition is in fact I less than m minus 1. Now, okay, so does everybody accept that, or does anybody object to that?
Are we going to get an example, like a full example, not just I guess implementing it into like how we've been doing it, just so we can simplify. I don't have any questions right now, just because
Sure.
I understand the concept, but I don't see it actually being applied.
Okay, well, yeah, the application, well, I have a toy application, and one of the main use cases for this is the situation is if we want m instances of an event, let's say A on the event list at time 0, for example. So here, again, forgot this. One of the differences, one of the nice things about the nice and not so nice things about these event graphs is because they're on paper, or in this case, in a PowerPoint. There's no NetBeans there to give you red squigglies when you have a mistake. So here this would give a red squiggly if there were a compiler for this. This would give a red squiggly because why? Because I'm scheduling an init event that has an argument, but I'm not giving it any value. So one of the main use cases for this is a situation where, and we'll, this is actually going to be I forget if I'm going to ask you to do this problem or not, but there's a situation, consider a shop where we have a bunch of machines. So let's say we have M machines in our shop, and what we're modeling is we're modeling their failures. So it's like they run, but then they fail. And when they fail, we have to do some stuff. When we start up the simulation, we have M machines. We want to have M failure events on the event list. This would be a way to accomplish that. So if A is the event that a machine fails, and typically in that we're going to say, let's say each machine has a certain failure time until they fail. Then to initialize our model, we want to put a failure event for each of the machines on the event list at the initial time. So that would be a use case. One of the use cases for this. In other words, situations where we want more than just a run event. We want other stuff happening. Now, as an example of passing parameters, and let's see, I'm not sure if this is exactly the same section as it used to be, but I haven't recoordinated it. Are you familiar? Have you ever studied like inventory models, or is that something they haven't? Okay, so I can speak completely freely about it. There's a term called periodic review, and it's the opposite of something called continuous review. So the idea in this is that we have an item, and we will only check that item's level periodically. And so we have these items, they're in inventory, and we periodically we have some customer who comes and wants them. And so we give them to them if we have them. And so there's a whole field of study for what are the rules in which we deal with this. And this is one of them. This is often called the big S little s model, or little s big S model, or the reorder point order up to. So the rule here is that we're not going to continuously be monitoring this thing. We're only going to periodically be checking it. Why? That's a story for another day. But the rule that we're going to follow is that when we check it, if it falls below a certain threshold, little s, which is often called the reorder point, then what we do is we place an order to replenish it that would bring the total inventory we have up to some big S value if it arrived immediately. In other words, one way to kind of, you wouldn't necessarily want to do this, but let's say I had a rule that I only check my gas gauge on Monday at 8 a.m. And other than that, I just ignore it. And if my gauge is below a quarter tank, then I fill it up. And then ignore it until next Monday and hope I don't run out. Okay, so now, obviously wouldn't necessarily do that, but that's kind of how this works. In other words, the deal on this is that the amount of items I'm ordering each time are going to be a little different. And the extra wrinkle in this is to be a little bit more realistic. If I place an order, then it's only going to arrive after a certain amount of time. And that's true even if it's Amazon. So, I mean, if I order it from Amazon, actually things are coming like the next day these days. But in some of the Navy items, the lead time for these things is literally years, which kind of boggles my mind. But in other words, when you place the order, it's not going to show up right away. Hopefully, eventually it does. Actually, some of the, I'm seeing some back orders that are also literally years. That are, this was supposed to come in 2015. It's still not here. What the hell? So, okay, so the customers are arriving at various intervals, and you can sort of think of that as like an arrival process, but the wrinkle on that is that each customer is going to demand a random number of items. So instead of just kind of one of, unlike the queuing model, each customer is just like one guy. But here it's like a guy shows up and says, I want 10 of them. And then the next guy shows up and says, I want 5. Okay? So if we have them, we can kind of give them. So guy shows up, I want 10, yep, here you go. Next guy shows up, I want 5, and he says, well, I only got 3. So what are we going to do? What I'm going to do is I'm going to give him the 3 and say I owe you 2. That's called a back order. When you've ordered stuff, have you ever been said, this is out of stock, but we're expecting them soon, and place your order, we'll send it to you when we get it, right? Should make sense. That isn't always the situation. That is, well, at least in the case of the Navy, NavSup has sort of a captive audience, as it were, because there's really only one, well, normally there's only one place where they can get the stuff. So on the other hand, like if I'm really hungry and I go to In-N-Out and it's like they're out or their thing is busy, I mean, if I'm really hungry, I'll go down to Burger King or something, So in this case, though, we're assuming we have a captive audience. So if we can't give it to them, we'll back order it. Okay, so like maybe I'm a rabid Apple guy, and so if they're out of my favorite MacBook or something, I'm gonna wait for it. Whereas if I'm a PC guy, it's like they don't have this particular Dell I want. Okay, I'll just get a Lenovo or something, Right, so here's kind of a little diagram of how this might work. So let's say at time 0 we started here, and again, it's actually going to be a little bit more random than this typically, but so what we have is this red line is, this is our inventory position. And the inventory position is going to be either how much stuff we have or how much we owe in back order. And so let's say it starts at this level, and then as customers keep demanding it, it kind of creeps down and down and down. And so what we have here these are the review periods. So here we're not going to check it until this first time. Let me change the pen color to be something else. Let's make it blue. All right, so here at this time we check our inventory position. It's above our reorder point, and so we do nothing until the next review period. So the next review period, we check it and we see, oh, it's gone below the reorder point, and so we place our order. So what this little dotted line says is, okay, now our net inventory position is actually up here because we are owed this many. And what's our order is like this, and then a little bit below there. Okay, so that's how much we order. And then sometime later, like right here, this is when it arrives. You see, so this much, and as we're waiting for it to arrive, our demand keeps getting chunked away until at this point we've actually gone into a backorder situation. So, but we're not checking it. And you say, why? You know, why? Well, there are reasons for this. So just bear with me. So here we're again. So even though, so here the order actually does finally arrive, and then we get this many items. So this amount was when we filled our back order, and then the amount up here is what we put in stock. And then by the time we check again, we see, we don't need to place another order, we're fine. And then things keep going on until this situation. Okay, so here we place another order, and we're waiting for it to arrive, and as we're waiting for it to arrive, we hit another review and we see, okay, we're in a back order situation, we're below our reorder point, and now we say, okay, what do we do? Well, if we just blindly follow that rule without remembering that there's an order on the way, we would place another order, and then Murphy's Law says they would both arrive and we'd have no room for them. Okay, so but here, so what we're checking is we're checking to see our net inventory position, which is actually up here, which says that even though I don't have any in stock, in fact, I'm in a back order state, I know that there are some on the way, so my net position is above the reorder point, so I don't place an order. Okay, so is the situation fairly clear? Okay, so we want to now let's model this. Again, the term is periodic review, little s, big S model. That's the terminology they use. You don't have to remember that. Okay, so parameters. There are actually quite a few parameters here. First, we have the time between demands, and that's sort of like an arrival process. But then, in addition to that, we have the number of items demanded. And so, in implementation, this would typically be a discrete random variable that would, because each one is going to be different. Now, we have the lead time for the orders placed. Now, when we place an order, it's going to arrive sometime later. We could model that either as a constant, but experience indicates that when we place an order, when we actually get it is not going to be the same every time. So we're going to model that also as a sequence of random variables, or a sequence of numbers, which we will typically use as a random variable when we actually implement it. Okay, some additional parameters. Okay, one is the time between reviews. Again, notice that there's no curly on this. Why? Because that's going to be a constant. So again, if I check my gas every morning at 8 a.m., then the time between this Monday at 8 a.m. and the time next Monday 8 a.m., that's a constant. So we're going to model that as a constant. And then we need some, to get this going, you say, how much do we have on hand at the beginning? So again, that would be another parameter. And then finally, these two values, the trigger quantity or reorder point and the order up to amount are both parameters as well, because those are going to be constant values throughout the simulation model. And typically, the question that we will typically ask of this model are, what values of little s and big S should we use? Because these are values that are completely under our control. This one is as well to a certain extent, but I'm sorry, the time between reviews. These are kind of out of our control. That is, how much time there is between demands, how much they demand, that's something that's a function of somebody else, that's not us. How much time it takes for us to receive our orders when we place, again, that's something that's a bit out of our control. But these are basically decision variables. And again, a common question on this would be, what are the optimal values of our trigger quantity and our order up to amount that would, okay, optimize what? Well, to put it in one of those models, we typically you would add costs to them because there's a certain, well, in practice there are often budget constraints which have to do not just with one item but with many. But when we look at the cost of inventory, typically if we have capital invested in stuff that's just sitting on the shelf, again, that's something that we don't want to do. If the items are such that it requires a certain amount of energy to kind of keep them, so if we have something that needs to be kept cold, then there's going to be an ongoing cost of doing that. We often have administrative costs of placing orders. In other words, you don't want to be placing a bazillion orders, because there's typically a cost associated with those. And then there are things like, there are kind of somewhat intangible costs, but that can be somewhat real in the sense that if we're in a back order position too much, we could put a cost on that. In the Navy, it's more of a readiness issue. So if we have aircraft that can't be flown because we're waiting for parts, I mean, that's a readiness issue. So it's hard to put a cost on that, so typically the models there are kind of looking more at readiness when we look at inventory types of positions on this. So again, continuing with our event graph model of this, again, we have state variables. So, there are a number of different ways of modeling this with state variables, but these are some of the things that we are typically going to be interested in. So one is going to be the amount that we have on hand, and that's initially going to be this. Remember, we said that I0 was our initial inventory level. So I is going to be the amount of inventory we have on hand, and B is going to be the amount that's backward, and we're going to assume that's initially 0. That initially we have some on hand, and we have a certain amount on back order, in this case 0. So, but one thing that we want to point out is that at any point in time, either I is 0 or B is 0. So what that means is if we have items in stock, then we shouldn't have any on back order, because if they're in stock, we would fulfill, we're going to fill partial back orders. On the other hand, if we have positive back orders, then we shouldn't have any in stock. So if I have 5 items in back order, then I shouldn't have any in stock, because I should fill the back orders. The total amount that we have on order, that's something that would be of interest as well. The total number of items that are ordered, again, that's something where for each item we have to pay for it. So again, in a cost model, we would want that. And then the total number of orders, and that gets at the idea of the fact that each time we place an order, there's a non-trivial cost to us. In other words, so we'd want to know how much of all these are. So let's look at the event graph. Would look something like this. So okay, here's our run event. Our run event initializes all of our state variables. Again, we can just immediately write that down. So there are 2 kind of arrival process-like events that occur. One is kind of the one most analogous to our arrival process would be an event, I'll call it a demand rather than arrival, because what's going to happen here is when a demand occurs, they are going to demand a certain amount, D, And so just one way of organizing how that impacts our state variables is to look at have a local variable called net, and that's going to be the amount that we have on hand minus our back order, so that gives us our net inventory position, and then we subtract the amount that the customer demanded, because that will either put us further into a back order position or just simply decrease the amount that we have. And so to update our on hand and back order, we take either the maximum of this net value or the maximum of 0 and minus that. So if you think about that a little bit, this will mean either net will be either positive, negative, or maybe 0. But if it's positive, then we still have some on hand. If it's negative, then we have 0 on hand and back order is now a positive. So here's where the review events occur, and what this kind of points out is that sometimes we have events that are there simply for the logic of the model, but there's no state transition, or more theoretically, the state transition for the review event is actually the identity mapping. And this schedules the next review, but then here's the thing. So let's kind of unpack this a little bit. Okay, what was T? T was the total amount that's on order. Yeah, so in other words, we need to, here's our Boolean condition. And the condition is, does our net inventory position fall below our reorder point? And so what is our net inventory position? It's the amount on hand minus back orders plus the total amount that we have on order. So in other words, if we know that we have some coming in, we don't want to keep reordering. So if that net quantity is less than our trigger point, then we're going to place an order. Now, how much do we place the order for? And that's where it gets tricky, because if we ordered the same amount every time, then we wouldn't need to worry about this. But in this particular case, I'm going to place an order, and my argument for the event placing the order is going to be how much I place the order for. So how much do I order? Well, here's my big S, my order up to amount, and I subtract my net inventory position from that. So I subtract the amount on hand, but now I add the back orders and I subtract the total amount on order. And that's how much I place the order for, and I pass that value to the place order event. And then the review event is finished, but then this is a 0 delay, so now I'm going to place the order. So what does placing the order do to the different state variables? Well, in this particular case, it increases the total amount on order by the amount that I'm placing the order for. It increases the total amount overall that I've ordered by that amount. And I increment by 1 the number of orders that I've placed. And then finally, I schedule the order arrives, passing that value with a delay of my lead time. And then when that order arrives, I now, what is the state transition? The total amount that's on order is decreased by the amount that was there. Again, I do the same calculation with the net, except now my net inventory position is increased by the amount that's been received, and then I update my amount on hand and my back order by the same amount. So the point of this is that this is an example of passing an argument, passing a parameter to an argument on the event, and the reason that's important is because the amount that I'm ordering each time could be very different, and I could have multiple orders that are pending. And so I could have more than one order arrives event on the event list, and when they happen, they will happen in the order in which they arrive. And when they arrive, each order will have as its argument the amount that was placed when it was ordered. Okay, so that's on the edges, and so for tomorrow, I will kind of keep reading some more. I'll put the exact thing on the on Sakai.